Hi guys, happy Friday. So we're going to pick up right where we left off yesterday with this graph. So yesterday at the end of the hour, we kind of started trying to put a title on this thing. And I had said that the dependent versus independent, of course, works just fine. But I think a better title here is probably describing that these are boiling points of molecular families. So if you look at this top line, okay, where I have hydrogen or water, H2S, H2SE, and then H2TE. If you look at oxygen, sulfur, selenium, and tellurium, those are all in the same family, meaning that they're all in the exact same column. Okay, so the shapes of these molecules are all going to be bent. If you look at the next series, we've got HF, HCl, HBr, HI, fluorine, chlorine, bromine, and iodine are all in the same family as well. These are just obviously two elements, so we have linear shapes with these four. We also have the nitrogen family here, so NH3, PH3, ASH3, SBH3. Those are all the nitrogen family elements bonded with hydrogen, and these are all going to be trigonal pyramids. Okay, so I'm introducing that because I want to use those shapes and talk about the types of intermolecular forces we have. So at the very bottom here, I'm asking to describe or discuss these types. So with bent molecules like the oxygen family of elements are going to make. These are all bent and they're all polar. Okay, that geometry, that bent molecular geometry, I'll draw it out. Okay, the bent molecular geometry of water is making this a polar molecule, and we know that, we've looked at that quite a bit. But the other three molecules, the H2S, the H2SE, and the H2TE, are all bent as well. Okay, so with a bent molecule, polar molecule, all of the water, the oxygen family elements and molecules, these are going to have dipole attractive forces. Okay, if you keep going down, HF, the next family, the halogens, when you have fluorine, chlorine, bromine, and iodine with hydrogen, these are all linear molecules, but that bond, if I look at hydrogen and fluorine, for example, okay, that bond there is a polar bond. Those electrons are not shared equally. Fluorine is more electronegative, pulls the electrons towards itself. Therefore, we end up with a partial negative on the fluorine, partial positive on the hydrogen. And these are also going to form dipole attractive forces because these are polar molecules. Okay, the ammonia, the NH3, PH3, ASH3, SBH3, all of those also are going to be polar. These are trigonal pyramid shapes because of the geometry. They form polar molecules. They're not symmetrical. They can't cancel out. Last but not least, the very, very bottom family there, this is the carbon family. So we have CH4, SiH4, GeH4, and SnH4 on the bottom. These are actually nonpolar. Okay? If you think about the geometry of CH4, which is methane, by the way, CH4 is a tetrahedral shape. Coordination number is 4, and the geometry here allows all of these bonds to cancel out. So we end up with a nonpolar molecule. The first thing you'll notice is, okay, well, if the top three series from the oxygen family, the halogen family, and the nitrogen family, if these are all polar, and the bottom one is nonpolar, you'll notice that, okay, polar bonds and the intermolecular forces that they have must be stronger than nonpolar intermolecular forces. Okay? So all three of these top series have dipole-dipole. And the bottom series only has London dispersion. London dispersion forces are generally weaker than other types of intermolecular force. And we see that reflected in the boiling points. The boiling points of the bottom series, only with London dispersion, are lower. What that means is it just takes less energy to break all of those intermolecular forces to turn it into a gas. Okay? All right, let's keep going. So something else you notice, and we pointed it out, but I didn't really talk about it. The water data point, the hydrogen fluoride data point, and the ammonia data point are all kind of off of our trend. And there's a reason why. Okay? So the criteria that must be met in order for hydrogen bonding attractive forces to exist is that the hydrogen must be bonded to one of three elements. And those are fluorine, oxygen, and nitrogen, the three most electronegative elements. When you have hydrogen bonded to one of those three, we get very polar bonds. And what you'll notice is these three are off of that trend because they actually have hydrogen bonding attractive forces, which get their own special designation. Okay? All of the other molecules in those families, these are polar, but you'll notice that they're much lower in their boiling points than the original molecules in each of those families. And this is why hydrogen bonding gets its own special name. Essentially, hydrogen bonding is nothing more than a dipole attractive force. But it gets a special designation because we see very unique properties when hydrogen bonding is present. So, to recap, hydrogen bonding is stronger than dipole-dipole, and it only happens when hydrogens are covalently bonded to fluorines, oxygens, or nitrogens in a molecule. All right, so the high electronegativity of these elements leads to a very polar bond and the molecule with large partial charges, aka it's more polar. Okay, hydrogen bonds are stronger than other dipole-dipole attractive forces and London dispersion attractive forces because of this greater polarity. If all attractive forces were created equal, you might think that the lower molar mass would have a lower boiling point. Thus, you would expect that HF should have a lower boiling point than HCl. However, all attractive forces are not created equal, and this is why hydrogen fluoride is said to have hydrogen bonding rather than the generic dipole-dipole. So let me recap. Hydrogen bonding is a type of dipole-dipole, but it's special because it's stronger. And again, it only happens when you've got a hydrogen covalently bonded to fluorine, oxygen, or nitrogen. All right, so let's keep going. With this graph, I also want to look at and explain why dipole-dipole forces are stronger than London dispersion forces. So again, we kind of see this general trend where we have these three families, the data from these three families higher up than the bottom family, and it's because of the types, all right? These three top rows, or these three top series, all have dipole-dipole. These are polar molecules, so the attractive forces are stronger, the partial charges are stronger, and this bottom one is nothing but London dispersion forces, okay? And they have lower boiling points because of it. So eventually today I'll give you, in your notes, you have a nice kind of breakdown of the stronger forces, the weaker forces, and the order they kind of go in. But even looking at this data for boiling point, we can see that, okay, London dispersion forces must be weaker because these are the ones that only have London dispersion, and they have the lowest boiling points. All right, so there's four family groups on the graph like I've been talking about for a little while now, and there's four members in each of these groups represented on the graph. The molecules of the carbon family are CH4, SiH4, GeH4, and SnH4. Each of these molecules has a symmetric or symmetrical shape and does not have a net dipole. And then therefore they have the lowest boiling points on the graph. Okay. And again, if they were polar, if they were not symmetrical and these polar bonds could not get canceled out, we would have a different type of intermolecular force. Because they're nonpolar, all we have is nothing but London dispersion, and those are the weakest. All right, so boiling point is related to intermolecular forces. It takes energy to overcome attractive forces and convert liquids into gases. Since the molecules with no dipole have lower boiling points than those with a dipole, dipole-dipole forces or dipole-dipole intermolecular forces of attraction are generally considered to be stronger than London dispersion forces. All right. On the x-axis, you'll notice also that the molar mass increases and that the boiling point for the carbon family molecules also increases as we go left to right. Okay. So this is going to relate to the London dispersion forces. If we go back to the graph, literally all four of these, apart from the first three here, these hydrogen bonding examples, Okay? But if we ignore these hydrogen bonding examples and we look at the rest of this trend, you'll notice that as we go right, we generally end up with a higher boiling point as the molecular weight increases. Okay? And this is going to relate to that whole polarizability thing that we talked about yesterday. Essentially, more molar mass is going to generally equal more electrons. More electrons generally equals a bigger shape or a bigger size of molecule. And as we get more stuff, or we have a larger electron cloud, we end up with a more polarizable molecule. And what we see as a result of that is that these boiling points, or in other words, the attractive forces between all of these molecules, okay, get greater. They get bigger as we increase that molar mass, as we increase the number of electrons present in that example. So let's keep going then. So the boiling point, since the larger molecules have a higher boiling point, there must be more attractive forces holding these molecules to their neighboring molecules. Okay. Therefore, for large molecules, we need more energy to overcome the intermolecular forces to boil the chemical species. As the molar mass of a family of molecules decreases, the electron cloud of these molecules is getting smaller. So I flipped the script, I apologize. We're going the opposite way now, so we're getting smaller. Okay, and the electrons are held more tightly as we get smaller, which leads to a less polarizable molecule and less London dispersion attractive forces and a lower boiling point. So again, to recap, essentially, more stuff, bigger molar mass, is going to equal stronger and bigger London dispersion forces. Partial charges are going to go up because of the more polarizable molecule. Extra space means we can push and move those electrons around further, which results in bigger partial charges. Okay, so London dispersion forces are instantaneous dipole, induced dipole attractive forces. I just want to recap what we ended up talking about yesterday. I'll go back really quick. So yesterday we were talking about this example of London dispersion forces. We have these electrons, they're moving around, and at some random instant they're unevenly distributed, right? And as a result of that uneven distribution, we get an instantaneous dipole, meaning at some random time we have a partial negative result here and a partial positive result here, just simply because of the electrons moving constantly and instantaneously having an unequal distribution. The result of that then can influence the neighboring molecule. This instantaneous dipole with a partial negative and a partial positive, the negative region will repel the electrons nearby and give us an induced dipole over here. I just wanted to recap that because I think that definition, or using those words, makes more sense than always simply just saying London dispersion forces. So let's go back and write that in. So London dispersion forces are instantaneous dipole, induced dipole attractive forces. All right, let's keep going. Bromine boils at 138 degrees Fahrenheit. Iodine boils, or has a boiling point of 363 degrees Fahrenheit. These are both halogens. Explain this difference. Now, I used freedom units, Murica units with Fahrenheit. Don't mind that. Essentially, I just want you to recognize that this one's bigger and that one's smaller, and I want you to try to explain why. First things first, bromine, pure bromine, does not exist as just an individual atom. It exists as a diatomic molecule. Same with iodine. Both of these are diatomic examples. So in reality, what I'm talking about here is Br2 versus I2. Okay, and the question is well, why? Why does bromine have a lower boiling point than iodine does? I'm going to pause the video, or I'd like you to pause the video And think about this, maybe talk to your neighbors about this, but try to give me a rationalization why we see these differences in boiling point. So go ahead and pause it now. Okay, so here's what's going on. If we look at bromine and we look at iodine, again, these are diatomic molecules, the reason why iodine's boiling point is so much higher is because of the difference in polarizability. These are both nonpolar, okay? Diatomic bromine exists as a single bond between two bromines. Diatomic iodine exists as a single bond between two iodines. But iodine is a much larger atom than bromine is. And as a result of that, the polarizability of this is much greater. So again, let me write out that explanation. Okay, so iodine is more polarizable, it's bigger, there's more electrons there, therefore the partial charges that result from this, from the London dispersion forces, are going to be bigger, and bigger partial charges lead to stronger attractive forces. That's Coulomb's law, and stronger attractive forces means that the boiling point is much higher. Okay, now this is going to be a little more abstract. But let's look at these two molecules. I have pictures down below, and these are called 2233 tetramethylbutane. Again, this is an organic molecule. This name corresponds to this shape, the right-hand shape in your picture. Okay, this has a lower boiling point than octane. Octane is the left-hand one. Now, these hydrocarbons, and by the way, the name hydrocarbon just simply implies hydrogen and carbon in a molecule. So don't lose sleep over that. But these hydrocarbons have a different structure, but they actually have the exact same formula. If you look at both of those pictures and you counted up all the atoms, you'd notice that they both have 8 carbons, and they both have, 18 hydrogens, okay? So the formulas are the exact same. This is actually called isomers. So these are isomers of one another. So since the molar mass is the exact same, our first guess is that they would have the exact same amount of London dispersion force. In other words, neither molecule has a dipole. Okay, both of these are nonpolar. The molar mass is the same. So in theory, we would expect that they're the exact same boiling point. But that's not what we see. The data actually shows us that the octane has a higher boiling point than the 2233 tetramethylbutane. So how can that be? Well, it has to do with shape, okay? So since these boiling points are different, we know that the substance with the higher boiling point must have more intermolecular force of attraction. Octane is much longer than the 2233 tetramethylbutane and exposes a greater surface to neighboring molecules. The greater the surface area exposed, the greater the London dispersion forces. 2233 tetramethylbutane is more compact. Okay, that shape, if you look over at the right-hand side, is kind of like a little ball or like a little sphere. It's much more compact, whereas the octane is elongated. Okay, that elongated shape, the big chain of octane, essentially exposes a greater surface area to the neighbor, which allows it to be a little more polarizable. You can think of it as. All right. So this 2233 tetramethylbutane is more compact. Therefore, there is less surface area exposed to the neighbor and less London dispersion force and a lower boiling point. So that's unique. Sometimes molar mass isn't the only indication of how or why the intermolecular forces are as strong as they are. If the molar mass is the same and if the formula is the same, like in this example, okay, we have to go a little bit further and we have to look at, okay, well, how are these actually organized or arranged? This linear one, this octane, just essentially exposes more area to its neighbor. So it's more polarizable in this example, leading to greater London dispersion forces, which leads to a higher boiling point. Okay, so use fluorine and whatever else you need to make a sketch that clearly shows hydrogen bonding attractive forces. Go ahead and pause the video. This shouldn't take too long, I hope, but pause it now if you could. Okay, so all we need is a hydrogen and a fluorine on one molecule and a hydrogen and fluorine on the next. Fluorine's more electronegative, so it gets the partial negative. Hydrogen is less, it gets the partial positive. Same thing over here. And then obviously as we have the partial negative of the left-hand molecule, that's going to be attracted to the partial positive of the right-hand molecule, and we get this hydrogen bond. Technically, this is also called a dipole attractive force because these are just simply polar molecules. But because the hydrogen is bonded to a fluorine, this actually gets that special designation of being a hydrogen bond. These are stronger than normal dipole-dipole. So just for fun, I'm going to draw in the dipole moment as well. Pretty simple, but this arrow would go like that, and this one would go in the same direction. Just showing the directionality of polarity. All right, so the more polar the molecule, the bigger the partial charges. Bigger partial charges are going to lead to a higher boiling point. That's just recapping again, basically what we've talked about for the last 2 days. The polarizability of the molecule increases with the number of electrons in the molecule. And actually, I haven't talked about this yet, but if you have pi bonding, and by pi bonding, what I'm really saying is if you have double and triple bonds in a molecule, that also increases polarizability. So more double bonds, more triple bonds in a molecule, if the molar mass is the same, or if the formula is the same, but one of the molecules has double bonds and the other one doesn't, pi bonding, or the one with double bonds and triple bonds, is more polarizable, and it's actually going to increase the attraction or the attractive force and increase the boiling point or whatever property we may be looking at. So the polarizability of the molecule is going to increase, like I said, with more electrons, and then those pi bonds actually can affect this too. Okay, so here's kind of a chart. This doesn't include everything, but if you kind of look at this spectrum, on the top side here we have London dispersion forces. What these really are intermolecular forces between nonpolar molecules. These are the weakest. If I go down this spectrum, you'll notice I have this big kind of section which are called dipole-dipole. So there's a wide range of polar molecules. And again, what's going to affect how strong these attractive forces are is based upon the partial charges. Bigger partial charges, stronger intermolecular forces. You'll notice at the tail end here of the dipole-dipole, we have a little region specially designated for hydrogen bonding. Hydrogen bonding is a dipole-dipole. It's just polar molecules, but these polar molecules have hydrogens bonded to either fluorine, oxygen, or nitrogen, and they do show different properties, and that's why they get a special name. And then last but not least, as we go further and further down, now we're reaching like ionic compounds, okay? So these are like ion-ion attractions. You'll see a 1+, full 1+, full 1-. And again, all of our intermolecular forces with these little partial charges are less than 1. So as we approach and get further down, these are full values of 1, which is a much stronger attraction. Ionic bonds are way stronger than intermolecular forces. All right, so here's some factors that are going to affect these things. What type of covalent bonds exist in the molecule? If you've got HF, HO, or HN, you can have hydrogen bonding. Okay, if there are any other polar bonds, then you may also have dipole-dipole. So we have to consider polarity. We talked about that last unit, but we have to also figure it out and use it this unit because whether or not a molecule is polar will affect the types of intermolecular forces it has. If it is polar, it's at a minimum going to have dipole-dipole, but it might have hydrogen bonding if we have the right type of covalent bond. If it's nonpolar, what we have are London dispersion forces. Okay? London dispersion forces are the really weak ones, the ones where the electrons are moving and we get an instantaneous dipole. That instantaneous dipole with tiny partial charges gives us an induced dipole on the neighboring molecule. Number 2, things to consider when figuring out intermolecular forces. How many electrons are present? Okay, if there's more, or if the molar mass is bigger, in general, we expect that to be more polarizable. More polarizability essentially is going to lead to bigger partial charges, which gives us greater intermolecular forces. And then last but not least, factor number 3, intermolecular forces. How will the shape affect the surface area? Okay, so in other words, the contact area. Long, skinny molecules generally have more intermolecular forces of attraction than molecules that are compact. So when comparing isomers, essentially we want to look at, well, what's the shape of those? Longer, skinnier ones will have greater intermolecular forces and lead to bigger boiling points and different properties such like that. Okay, we're on to the final table. What I would like you to do is I'm going to draw up the shape for some of these because I did not provide the formulas here, so I'm sure you would like to know what, for example, ethanol is, or what propane 1,2,3 triol is, because I have a hunch you don't know that offhand. The other ones you should be able to get, but let me draw in these 2 shapes. And what I would like you to do is I would like you to fill in this chart. Please take your time. Pause the video and take time talking to each other and trying to figure out the types of intermolecular forces that you have. I've got 4 options: London dispersion forces, okay, dipole-dipole, and hydrogen bonding. The last one I have over here is ionic. Technically, ionic is going to be an intramolecular force, but I did sneak a couple of ionic compounds into this example. So when you have an ionic compound, we don't have to worry about the intermolecular forces. So let me give you those 2 structures of the ethanol and the propane 1,2,3 triol. You'll need to think about the shape of these molecules. Are they polar? Are they nonpolar? And that'll kind of lead you to these answers. Yeah. So ethanol is going to look like this. Okay. It's 2 carbons in a chain, and it has an alcohol group, which is an OH group, off of one side. The alcohol group is going to be polar. Okay, I'll give that away. So this oxygen there is very electronegative. It's going to pull the electrons towards itself. These carbons over here all have hydrogens hanging off. And there's 2 more hydrogens right here. Okay, but that's ethanol. It's a 2-carbon chain with an alcohol group. 1,2,3, or propane 1,2,3 triol is going to look like this. It's a carbon chain of 3. And each carbon has an alcohol group coming off. So this one has an OH, and this one has an OH, and this one has an OH. And there would be 2 hydrogens hidden here, another hydrogen hidden here, and one last, or two more hydrogens, I'm sorry, over here. Okay, and again, those little alcohol groups are polar. So, okay, at this time, please pause and work on this chart. And again, take some time, try to get these correct, think about them, talk about this with your neighbor, and fill this out to the best of your ability. I'll come back in just a little bit and fill it all in. Okay, so let's look at ammonia. Ammonia is NH3. All right, NH3 has 1 lone pair on the nitrogen and 3 hydrogens coming off of it. That's a coordination number of 4. But we only have 3 bonds and 1 lone pair. This is going to be a trigonal pyramid. So this is going to have certainly dipole-dipole attractive forces. Everything, by the way, has London dispersion. So we can put yes in more than one column here for ammonia. It has London dispersion because everything does. It has dipole-dipole because it is a polar molecule. But if we analyze the types of nitrogen and hydrogen bonds in ammonia, you'll notice that the hydrogen is bonded to nitrogen. That's one of those special instances. That's one of the special cases where we do have more than just dipole-dipole. We've got hydrogen bonding. So that's also there. This is not ionic, so we don't have that one. And what I asked you to do was basically circle the strongest force present. Well, I've organized it pretty nicely from left to right. The furthest one left that you have yes for, that's your strongest. All right, so dibromofluoroborane. We did an example of dichlorofluoroborane yesterday, and we analyzed this, and I'll actually go back and use that as my picture here. So here that is, okay? It's a polar molecule. It's trigonoplanar, but we don't have the same things around the outside. We get a polar partial negative, polar partial positive, with a dipole moment like this. No hydrogen anywhere, so this is not hydrogen bonding. This is simply just going to be dipole-dipole. But we always have London dispersion as well, so we have yes and yes in the last two columns. I'm just going to start writing Y to save myself some time. And the strongest there is going to be the dipole-dipole. Fluorine, and when I say fluorine, I mean diatomic fluorine, F2. This is nonpolar. It's a fluorine bonded to another fluorine. We've only got one type. This is simply London dispersion forces and nothing else because it's a nonpolar molecule. Francium fluoride. Here's a sneaky one. This is an ionic compound. It's got ionic bonding. Okay. If you want to say it has London dispersion as well, perfect. That's fine. No big deal. But the ionic bonds here are going to be much, much, much stronger. It does not have hydrogen bonding. It does not have dipole-dipole. Ionic bonds are unique. Remember, ionic compounds make these lattice structures. So they don't really have intermolecular forces because of the way these cations and anions kind of arrange themselves. But I'm perfectly okay if you said that it did have London dispersion forces. Sulfur dioxide, this is SO2. The Lewis diagram from this one, you may have had to have drawn it out. If you didn't draw it out, you might have gotten it wrong. But sulfur dioxide has a lone pair on the sulfur and two oxygens doubly bonded on either side. So as a result, we get a bent shape. That bent shape leads to a polar molecule, which means we do have dipole-dipole, no hydrogen present, so it can't be hydrogen bonding, and London dispersion is always there. So we end up with both dipole-dipole and London dispersion, the strongest being the dipole-dipole in that example. Sulfur hexafluoride, this is a octahedral shape, nonpolar molecule. That geometry leads us to completely canceling out of all the fluorine and sulfur bonds, So we have nothing but London dispersion here. The ethanol that I drew down below, ethanol's got that alcohol group, that oxygen, that OH group coming off to the side. That is very polar. So the electrons in here are getting pulled towards that OH group in this molecule. As a result, this is polar. We certainly have dipole-dipole. We always have London dispersion. And we kind of have to think, do we have hydrogen bonding? Well, we've got an oxygen. We've got at least one hydrogen bonded to it covalently in our shape. We do have hydrogen bonding here. Okay, so we're always on the lookout for hydrogens being covalently bonded to either fluorine, oxygen, or nitrogen to kind of pick out those hydrogen bonds. Carbon tetrachloride, this is CCl4. This is a tetrahedral shape. This is nonpolar. It's a symmetrical geometry. All four chlorines are equally spaced in three-dimensional space. The bond angles here are going to be 109.5, and this is nothing but London dispersion. Propane 1,2,3-triol. This is the other one down below. We've got three alcohol groups, and again, these are polar. These alcohol groups, or these O's, the oxygens in these alcohol groups, are pulling the electrons towards themselves. So there's no way we can cancel out this shape. It is a polar molecule. We do have, at a minimum, dipole-dipole. We always have London dispersion. And because the oxygen is bonded to a hydrogen and vice versa, we actually get hydrogen bonding here as well. And last but not least, phosphorus trihydride. Phosphorus trihydride is actually going to be in the exact same molecular family as the ammonia that we started with. So this is a trigonal pyramid. If you do the Lewis diagram for this one, you'll get a lone pair on the phosphorus, three hydrogens bonded to it. We've got a coordination number of 4. Coordination number of 4 with 3 bonds, 1 lone pair, leads us to a trigonal pyramid. This is a polar molecule. We do have dipole-dipole. We do have London dispersion. But in this example, we don't have hydrogen bonding because the hydrogen in this example is only bonded to phosphorus, not one of the 3 most electronegative ones, fluorine, oxygen or nitrogen. So that's it for today. Thank you guys. I hope you were on your best behavior. Please work on your homework for the remainder of the hour. If you're going to go take the exam or retake the exam from Unit 2, please let the substitute teacher know. They'll sign you out and you can do that. Otherwise, work on your homework. That is going to be due on Tuesday. And you also have a couple online assignments on the AP Classroom that you can work on as well. Please do those. Once you finish all the chem, I would ask that you just stay on task and do something of value related to school if you could. Have a great weekend. We'll catch you guys on Monday. See ya.